Yo, okay, what's up? My name is Menace. This is a Grad Algos study stream, part 2. Cool. Uh, we'll pick up where we left yesterday. This is CS After Dark. So, again, we're just gonna start studying again. Did Loki waste my entire day? Because there's very little reason for me to keep studying. But there's life goes on, I guess. That's the only thing I can say. Cool, it's 10:02, and let's see. Let's start. This is our study plan. So let me do this. Okay. Timestamps. Let's just say day 1, day 2. Cool. So started live and started coding. Okay, started live and started planning. Okay, cool. So we need to go through PDF 17 to 13, which is fine, I guess. Ain't too bad, right? So that's fine. Yeah, can't believe that I'm graduating. This is kind of fun, not gonna lie. Hold on, let's see. Thinking. Let's see. Thinking. What should I do? I'm just thinking I do need to do yeah, I do know that I need to do some sort of like I do know that I need to go through my flashcards. I'll probably do that soon. Yeah, there are a lot of things that I need to do. Okay. No, that's crazy. This guy is like a PhD researcher at Georgia Tech, and now he went to. Okay, man, that's really aura, man. That's just aura, I'll say. What's this dude working on? Research fellow at Adobe, fine. Sure, Gaurav Verma, sure. Let's see how many people from OpenAI actually are from Georgia Tech, for example. Let's see people. Okay, let's say where they studied. Stanford, Berkeley, MIT, Cal, SEMU. There are some from And there's some from Georgia Tech, I guess, which is pretty decent. Okay, I love this Chetan Kali kid because he's just legendary. What does a non-degree option even mean? Right, that's interesting. That's pretty interesting, sure. Maraddu Khan, Amelia, building age. Yeah, that's so cool. That's so cool. I'm just like checking Georgia Tech alums who are currently working at uh, OpenAI, for example. Okay, that's so cool. MTS just 4 months ago. That's really good, honestly. Where's Anthropic? Let's see, Anthropic people. I'm looking at people, honestly. Stanford, UCLA, Wharton, Cornell. That's fine, I guess. Okay, most of Stanford grad, but makes sense because it's from because it's like in Seattle, I guess. Okay, I love this guy, Tony Wang, because this is just aura, man. Yeah, I love this dude, man. Did a PhD. Okay, I see. This guy has a. I'm just like studying profiles right now, just to get some interest, I guess. What is this thing? Okay, that's interesting. That guy's working on some fun things. Sure. Yeah, I love this. He is boy at Anthropic. You see, that's like a mark of a legit goated. This is how goated employees are, I believe. Like, became an MTS. Pretty good. Pretty good. I'm gonna stalk these people, because they look very fun. Random data stuff. I love this. At Anthropic. I love this Isaac O. Oh, I love this. Oh wow, this good dude is like building some shiz, bro. Rekha Citadel, Monad Labs. Okay, this is classy, I would say. This is like high signal shit. Okay, I love this, honestly. Hold on, I'm just gonna. Uh, hold on. I'm right here. I'm right here. Let's just see. Online presence for Max Aura. Cool. So these are just like post Isaac. Okay. Okay, I'm just gonna do this. Okay, fine. I love this. Pursuits. Where is the other sandal, bro? Okay, cool, fair. Fine, Isaac. Let's see more people, I guess. Barry Zhang, I love Barry Zhang, is just very minimalistic. So, okay, so very impressive is Barry Zhang because he has absolutely no signals. It's like Northwestern, some research engineer, Venture Scout, and MTS. It's so cool, bro. Eugene Hua is UCLA. There's way too many UCLA kids in this. Isn't this the brother of Jason Wei? Okay, this is also Aura, honestly. I like this. Okay. Okay, Tony Wang is one of my favorites because he's just like super, super aura-inducing person. Tony Wang, sure. Neha Kumar is okay. So she's applied AI at Anthropic. She's also from UC Berkeley. Okay, but okay, I get it. She's been in the industry for a while. Let's see, Rachit. Why is Rachit saying that he's in? Oh, he's an investor in Anthropic. He's a Series B investor in Anthropic. What? How? Dude, he's an investor in everything. How is he an investor? How is he getting on the investment round? That's crazy. Nah, dude, how are you doing this? Again, I'm very impressed with this because he's making mad money now. Sure, Matthew Stone looks fun also. Lucas Windstorm also looks fun. Patrick Wong looks fun also. Okay, I got one NYU kid in Anthropic, I guess. A very slow website, to be honest. Honestly, I don't like it. Okay, I like this Lucas Sis profile as well because it's Aura. Patrick has nothing to add here. Okay. No, I love this. This guy is Aura because this guy's been doing something outside of work. He has a blog called Save Buffer, which is also pretty cool. Let's see. Pretty cool. That's pretty cool, I guess. I'm looking for someone goofy. I'm looking for someone like non-serious aura. I don't see a lot of aura from these people. This guy seems to have a lot of aura, man. Cause it's just like funny profile. I like this. Okay, this also looks fun. Sure. Okay, hold on. I absolutely love this because it's just funny. Where's OpenAI, bro? Let's see. Wahid Kazemi, fine. Sure, bro. This guy's cool though. Aura. Okay, I'm just checking out her profile. Oh, come on, Josh. Wow. I love her. This is Pune girl. Winning in life. Yeah. Cool. Gauri Shankar looks cool, honestly. What is this about? Interesting. So, see, a huge amount of people. Wow, that's crazy. Kenzie T. Sure. Interesting. This guy looks fun, honestly. Mm-hmm. Okay, cool, fine. So, okay, like this. This is so cool. Pretty cool, honestly. Okay, pretty cool, I guess. Okay. Okay. That's a lot of stuff here. Not gonna lie. Not gonna lie, dog. What is this keystone here, I think? Okay, cool. No worries, it's just gonna be brutal, but fine. The study session's gonna be brutal, is what I'm saying, bro. Okay, 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 okay. Okay, cool. I think this is good enough. Sure. Sure, sure, sure. Oh, I didn't do the thing that I was trying to do in the first place. Uh, okay. Not gonna lie, dog. That's crazy. I get it. I get it, dog. I get it, dog. What's going on here? Wow, that's nice. We gotta study though. Okay, okay. 0 views, that's good. Okay, so what's the time? So it's like wasted time scrolling on LinkedIn and didn't do jack shit. Classic Shiv move. Woo! Okay, dog. So let's see. You know you need to do the duality stuff here. And cool. So what I can do is I can finish all the PDFs. Okay, cool. What I can do is I can finish all the remaining PDFs, which is whatever these are. I don't even, these are not numbered unfortunately, so I can just finish going through these PDFs. So LP and dynamic programming parts are a bit, I would say, important, because not important, they're the only ones that I need to go through carefully. And once I've gone through them, I think we should be okay. Okay, anyways. Okay, let's go here. And of course, like what I'm gonna do is, I know I plan to sit here for a long time. So these would be 4, and let's see what other PDFs I have lined up here. So 14th is simplex, 15th and 15, 16, 17, 18. And okay, so 14, 15, 16, 17, 18. And 19. So 6 more PDFs for till set, and then we have like 5 more, and then so the last 5 are gonna be a challenge. So I think like till at least set and OV. I think I should at least finish everything till Seth and OV, maybe, because that should be like the main focus. Like Seth and OV. Let's see how far we have come here. We got no analytics on 8th of December, but fine, we're okay with it. Bro. Cool. So linear programming. I'm gonna just get myself a snack while I study because just tired. Of course, I need to do. I do need to do um, flashcards, so I'll do that too, I guess. I'm good. I just got a 2 packet of Lay's. Thank you to the vending machine guards, I guess. Cool. So, time to lock in, I guess. Should I go refill my water bottle maybe? Could do that. Let me do that. Let me do that real quick, bro. BRB in a few minutes. BRB, baby. Sorry, just being retarded, bro. Okay, cool. We're back. Okay, cool. So, absolutely despise studying because, yeah, why would I want to do that, right? Like, Anyways, this is about the proof of optimality. Suppose you have an LP. Friend claims they know some optimal solution X star. Can they prove to you that X star is optimal in polytime? Okay, X star is the optimal solution. Okay. Okay. Proving it, this is just verification. You're just taking like a linear combination of all the constraints and you're saying it, hey, okay. Now we talk about duality. You know the for primal. Okay. Your A is gonna be some M cross N matrix. M is the number of wait, hold on. N is the number of variables and M is the number of constraints. Is that what we have? Gotta be right. Yeah, that's what it should be. Sure, makes sense. And you have an xi, which is sure. Okay. Then you have a dual LP where you say, okay, there's a y, which is y transpose b. Okay. 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 I see. You know what? Let's do this. Not this. Not this. Not this. Oh no, not this. Actually, this is the old exam, I think. I don't want the old one. I want the latest exam. Makeup exam without the solutions, maybe. Yeah. I know this has like a LP question. I'm just gonna try to solve it because it's like a duality. Okay. So let's see. Okay. I'm gonna try one thing, okay? Okay. Okay. Remove this outside, I guess. Back over. What I'm gonna do is I'm gonna delete this shit. Okay, and random. I'll just say, and I'll just say cool. So let's go to this question that we had here. Okay. Okay. Oh, come on, dog. Delete this shit. Clipboard. Yeah, let's do this maybe. Cool. So this is like one of the questions, right? So let's see. Right, we gotta write a dual for this. So general equation for a primal is max C transpose X, let's just do max Cx, such that A transpose X less than equal to B and X greater than equal to 0. This is how your primal looks, right? And your dual is essentially like min by such that ya c sorry, it should be, I think, less than, I guess, y. I think this is how it is. Again, I could be jogging my memory, but if I were to map this all, right, my C now becomes 1 2 1 4. So 1 2 1 1, sorry, 1 2 1 1, and you can see there 1 2 3 4. So the four variables, so n is equal to 4, m is equal to, let's see, 1 2, I have 3 constraints, so m is 3. So my A is going to be like a 3 cross 4 matrix. So my A is essentially going to be yeah, let's see what my A will be like. So it will be 1 2 1 0 1 2 1 0, because the coefficient of 4 is 0, and they've properly laid it out, so just to make it easier for us. Then it's 0 1 0 1 0 1 0 1, and then they have given 1 0 2 0. So 1 0 2 0. So this is like the third. So this is like a 3 cross 4 matrix. We know that B in general, the B matrix is also like a matrix which has a total of 4. Sorry, it should have total of 3 entries, because its size should be like 3 cross 1, right? So it will be 2 1 1, right? It will just be 2 1 1, and this is straightforward. Cool. So we know, okay, so num vars in primal equals num constraints in dual. This is what we know. Num vars in num constraints in primal equals num vars in dual. So our dual essentially is going to be min of you know, it's by, right? So 2y1 plus y2 plus y3, such that the constraints are going to be simply we're just gonna have like 4 constraints this time, and this is the RHS for the constraints. So this just becomes a transpose now, right? So this just becomes like a transpose for this just would become the first column basically, right? Which will be y1 plus y3, right, greater than equal to 1. Then it will be 2y1 plus y2 greater equal to 2. Then y1 plus y3. Interesting. 2y3 greater or equal to 1. This is the one. And then the last one would be y2 greater or equal to 1. And y greater or equal to 0 for all yi. This is what we should expect, I believe. Now the thing is, I'm not very sure about the equality thing. Right? So let's see. Let's see what the example says. I'll just paste the okay, so correct answer is this: min 2 y1 y3. This is correct. y1 plus y3 greater than 1. Okay, so the greater than sign is correct. 2y2 plus 2y1 plus y2 is greater than 2. y1 plus 2y3 is greater than 3. y2. Okay, perfect. So we got this question right. This is perfect, right? So this is the answer, which is good. Let's see what the second part of this question was. Prove that x1 equals 1. Okay. This is a question asking, oh come on dog, asking me to prove something. So prove that x1 equals 1, x2 equals 0.5, x equals 0. Okay. 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 So okay. Bro, come on, bro, don't do that to me, bro. Let's see. Okay. So I gotta prove this shit. Okay, to my LP was this. Okay. Can't even load this for some reason. Anyways, so I can, it's the optimal solution. How do I prove that something is an optimal solution? One is if it's like a feasible solution, maybe, right? Woo! Okay, went in the trash, which is perfect. Cool. So, how do you prove this? I know in order to prove that something is optimal, one thing I could do is I could just plug the values in, right? So, I know the maximization is x1 to x2. Okay, so it's just x1 plus 2x2 plus x3 plus x4. If I plug these values in, it's just going to be 1 plus 1 plus 0 plus 0.5, which is just 2.5. Now the question is, x equals 1 is, I know all of them are greater than 0, so they satisfy this constraint that your variables are greater than 0. Now for x1 to x2, okay, so if I do x1, 1 plus 1 plus 1, sorry, 1 plus 1 plus 0, x3 is 0, right? So 1 plus 1 plus 0 is feasible. So it's feasible. 0.5 plus 0.5 is 1, which is less than equal to this. 1 plus 2 times 0.5, okay, 2 times 0, so 0.5 is less than 1, so it's okay. So these values are feasible. So these values are feasible, and I think in order to claim that these are optimal, you can just say that these are tight constraints, right? I could say that if I go to first, like 1 plus twice of half is 1, plus 0 is 2, 2 is equal to 2, so this is the first constraint is tightly matched. Then the second one is just 0.5 plus 0.5 is equal to 1, which is also tightly matched, and 1 plus twice of 0 is 1, again tightly matched. So okay, the values are okay, the values are feasible and tightly satisfy equality all three constraints, so it is an optimal solution. So let's see what the actual answer is. Well, okay, this is interesting. Okay, the actual answer, okay, use a dual to construct the optimal value. Please do this. So instead they use like a dual to create find an optimal value, and just argue that consider the dual solution this. Okay, fine, sure. Okay. Okay, so this is not enough. You need to show that the dual optimal for dual also. Okay, you need to show that the optimal for the dual will also occur at the same value. Okay, cool, got it. I get it. I get it now. So what I can do is, in this thing, the only thing that I would say is of some importance is the only thing that I think is of any importance here is let's see, let me go through my cheat sheet and see what were the things that I had noted down last time, because those are probably going to be the same things that I will add this time as well. This is the notation cheat sheet. It's just fine. I'm just going to keep this aside. This is the last one. I need this one, correct? Okay, so Okay, let me see what all things I covered yesterday in my blog. Uh, for any LP, there exists some non-negative linear combination of constraints such that LHS objective value equals RHS objective value. Okay. Okay. Sure. Fine. Whatever. Okay. This is also something that I've recorded. Okay. I need to add LP duality now. So I'll just make this. Okay. So primal LP is gonna be of the form max C transpose X text. What if I save this as a draft? How does this render? No, it just does not render well. Primal LP, I'll just say objective, because this is gonna be easier to render, I would say. Primal LP constraints are gonna be AX less than equal to B, right? And X and it's going to be X greater than equal to 0, I believe. Then we'll just do dual LP objective. Okay, of course. We got a primal LP has n variables and m constraints. We'll go to now dual LP objective. This is gonna be like a min of B transpose y basically. 5 dual LP constraints. These are gonna be but this time it's gonna be greater than equal to some C and like some Y greater than equal to 0, right? And we'll say dual LP has m variables and n constraints, right? Come on, save it, dude. Okay. We'll now write down the theorems. Weak duality theorem. Feasible X for primal LP. Feasible Y. Okay, you know what? I'll just do this in dollar signs. I know you all are not gonna see this on the stream for dual LP, but I don't care that you don't see it. It's just like me holding myself accountable by streaming. Then optimal primal value is optimal dual value. Okay, optimal primal value is always less than or equal to dual value. Optimal dual value. optimal dual value. So this is basically saying C transpose X is always going to be less than or equal to B transpose Y. This is the weak duality theorem. So C transpose X is less than B duality Y. And there's a corollary to this. Let's see. This is strong LP duality, fine. We don't need to worry about the proof of strong LP duality. Okay. Okay, let's do that, right? Now I can just say that, hey, listen. I can be like, okay, weak duality corollary. If we find feasible X and feasible Y, where C transpose X is equal to B transpose Y, then X and Y are optimal. Then X and Y are optimal, okay, fine. If primal LP is unbounded, then dual is infeasible and vice versa. Okay, so if primal LP is unbounded, then the dual is infeasible and vice versa. How do we know if primal LP is unbounded? You can create a slack variable z and try to see if z is, you can try to maximize z, and if max value of z is negative, then it's unbounded, right? Oh no, if you want to find if it's infeasible, if you want to find if it's unbounded, you can just do its dual, same thing with its dual, and see if it's unbounded. Sure, that should work. Cool. And then we come to the strong LP duality, which is strong LP duality theorem says if primal LP value is finite, then optimal value is the same. Okay, hold on. There's some difference in, if the primal LP value is finite, then the optimal dual LP value is the same. Optimal dual LP value, right? Okay, got it. I kind of missed this in my notes, I guess. So guess I can update it. Then optimal dual value is the same. If the primal LP value is finite, then the optimal dual value is the same. Or you could just say primal LP is feasible and bounded if and only if dual LP is feasible and bounded. That's basically the Brito lecture that we had. Anyways, that's cool, I guess. But that's fine. Okay. Sure, this is like the weak LP duality or something. No, this is the strong LP duality again. We have Farkas lemma. Okay, this is like an important one. Farkas lemma is like an acts as a certificate. There exists X in to the power n, right? There exists some X that belongs to some n-dimensional real number space such that ax equal to b, okay, and x greater than equal to 0. Sure, that's like one of the common requirements is infeasible, then there exists a y such that uh, y transpose a greater than equal to 0 and y transpose b less than 0. Okay, got it. So this is like Farkas lemma, I guess. I know there was like an exam question for this. So if if we have this tight constraint that ax equals b and x greater than equal to 0 is infeasible, if we say that this is infeasible, then there exists some y such that y times a is greater than 0 and y times b is less than 0. Okay, so you are saying that, okay, Farkas lemma is a certificate of infeasibility. Sure, got it. I'm just gonna like Farkas lemma is a certificate of infeasibility, right? So what I'm saying is that if I want to see if a LP is infeasible, then I want to find a y what it would do is, if I multiply y with its coefficients and y with the RHS, like if I have constraints ax p, if I separate out the A matrix and B matrix, and I managed to construct a y such that a y greater than equal to 0 and a b less than equal to 0, then it means that, hey, your LP is infeasible. Cool. That's fine. Then there is this random theorem here which says theorem says there exists a polytime algorithm to check LP feasibility. Then there exists a polytime algorithm for LP optimization. Okay, interesting. So if you if there exists a polytime algorithm to check LP feasibility, then if there exists a polytime algorithm to check LP optimization. What does this even mean? Okay. So if you check if a hold on, thinking. Okay, I get it, I guess. Okay, I get it, dog. I get it, dog. $11, $12. Okay. 11. No, not this. Random में जाते हैं. How about 10? Let's see. Okay, can I recite it without looking at it? I'm saying that if there exists a polytime algorithm to check the feasibility of an LP, then there exists a polytime algorithm to find an optimal value for that LP. Is that what it's saying? Okay, cool. Okay, so this PDF is pretty much done. We're done with 11th. So let's just see, timestamp it again. Oh wait, hold on. When did I finish PDF 10 though? Hold on. 9, 10, 11, 12, 13. Okay, I finished PDF 10 actually, not 11. My bad, bro. My bad, bro. Brampton ਵਿੱਚ ਮੁੰਡਾ ਰਹਿੰਦਾ ਕੁੜੀਏ ਪੰਜਾਬੀ ਨੇ What is this thing doing? Okay, this is just like an example run, which is fine, I guess. Ah, this part's dynamic programming. There's ain't a lot to do in dynamic programming. This one's like pretty easy, I would say. I will, however, write some basic results for dynamic programming. Dynamic programming, I guess. Mostly I need to do in dynamic programming. I just need to do the Markov decision process thing, right? Okay. Anyways, so I find define a subproblem, store it in some array, use solution of subproblem to solve the current problem. Okay, longest increasing subsequence. Input is an array with n numbers. Fine. It's a subsequence. So subsequence and subset are different things. Subsequence. A sequence is it continuous? No, it's not continuous. Longest increasing subsequence. So I just need some subsequence that's just increasing, right? Brampton which mundaranda ਕੁੜੀਏ ਪੰਜਾਬੀ ਨੇ Brampton which mundaranda. Okay. Sorry, let's focus again, please. Focus. Super mama ready. 1 2 3 pa 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 pa. Girl, you are dying now. You showed me power. Anyways, I'm opening my third packet of Lay's because I'm hungry. And I hate the taste. I'm repulsed by it, low-key. Okay. Sure. Okay, hold on. So this is one. There's a knapsack problem, which is fine. Okay. 1, 2, and 3. 1 2-sided cheat sheet allowed. Okay. I know this is disgusting. Making sounds while you eat. Okay. What I can do is I can quickly finish this PDF. Make notes. Not too hard, honestly. So long as increasing subsequence. Okay. So I can just define at some table I ti. I can define my ith value as the longest increasing subsequence that includes the ith element, right? So what is it gonna be? You could either say this current element, if it is greater than but wait, subsequences do not need to be continuous, right? So one strategy that I can think of is think of if T of I is the longest increasing subsequence that includes the ith element, then if you go to Ti plus 1, if Ti plus 1 is greater than Ti, sorry, if Ai plus 1 is greater than Ai, then it means that Ti plus 1 is just Ti minus 1 plus 1. Sorry, it's just Ti plus 1 is just Ti plus 1 because you're including it. Or what does it mean if Ai is greater than Ai plus 1? It means that the value stored at Ti okay. Well, let's see. There exists an O(n) square algorithm. That's what I was thinking. You create a 2D matrix, sure. As you look back, complete. So good, so good. Okay. Okay. Uh, Come on, dog. 1, 2, 3, 4. Okay, hold on. So if A. Okay. I can create a 2D uh, graph, 2D matrix like this, sure. Sorting all the values for some reason. Like, who gave you the right to sort it, bro? Okay, sorting it as n log n maybe. Sure, which is less than n. Okay, thinking dog. Mm-hmm. Brampton Vichamunda. Wow. Okay. I'm just trying to figure out LIS for my own. I had a different formula than the one given in the lecture because it's just stupid. Like, why would I do that, right? AI greater than V, maybe, sure. Hmm. You know what? Brampton Wichmundarenda. My n-square solution is easier actually. No, I'm very serious. Yeah, my square solution seems much better, honestly. Yeah, I'm not gonna use such convoluted bullshit solutions to do my things, bro. Yeah, bro. Fuck it, bro. Fuck it, bro. So yeah, so I'm not gonna waste my time implementing some bullshit solution like that they expect us to write. Python LIS. Big of n square solution. Come on, dude. Save. Why ain't it saving, dog? Okay, so as long as the conclusion remains the same, that the optimal is big of n square. They said algorithm takes n square space and n squared space. I can just do it in n squared time but linear space. I don't need to do like a, yeah, I don't wanna do, sure, whatever, bro. So then there is the max independent sets, which is given graphs. You just need to figure out, find the largest set that covers. Okay, this is the set cover question, right? So for some vertex, it's just gonna be max of 1 plus uh, its child, if child belongs to grandchild of V, because that particular thing covers. Okay, okay, that's pretty straightforward, though. Let's see, max independent sets. Find a set S that find a set S which is a subset of V such that uh, okay, largest independent set. So what does that even fucking mean, bro? Goal, given a rooted tree, find the size of the largest independent set V that belongs to V, which means, okay, this. U and V do not belong to edge E, such that for some edge UV in S. Honestly, I'm just gonna write this down because I don't know this shit at all. I don't think this is valuable. I can figure it out from scratch because I don't think it should be this uh, max independent sets on trees. Sum of MU MU for U in grandchild of V it's the max of these two, right? This or child of V. Yeah, just child of this. child of V, not U. Okay. If you and child of V, sure. So okay. So if I start with the root would just go and say okay, 1 plus, essentially saying you include the root and directly go to the grandchildren, which is you include this and directly go here, or you start here and just include the child. So okay, makes sense. This is like a DFS. Runtime is big of n. Runtime is big O of n, I believe. Okay, so I'm just gonna make a comment here. Includes the root, excludes the root. So this is okay. This looks pretty good, I guess. Now, pretty straightforward. Correctness just usually in. Okay, I'll just write a tip here. Tip for exam, present solution in form of base case inductive step, induction step, and table structure. Okay, table structure, base case, and runtime complexity. These 4 things. Cool. Next, so we just finished PDF 11, I believe. So 11:35 p.m. is what? PDF 11. Let's just see. We did dynamic programming, LIS, max independent sets on trees. That's all we did, honestly. Cool. Let's see 12th. What does 12th do? Knapsack. Okay. Brampton no Wichimunda. Okay, so we're gonna do like knapsack using dynamic programming, which is cool. Let's see. So we are given a budget B and some n jobs, size I, and value VI. We're gonna find A that belongs to n, subset of n. Okay, such that SI is less than BI and maximize the value. Okay, got it. So we're given a budget B, and our jobs cannot exclude, the n jobs just cost S of I in terms of time or something, right? So sum of S of I should not exceed B, and the maximum value should just be, you should just maximize the value. So it's okay. Okay. One thing is, note that knapsack is a NP hard problem, and hence we don't think it's solvable in normal time. Okay, so we do have a pseudo polynomial time algorithm. So hold on, first of all we'll do poly time versus pseudo polytime algorithms, maybe. which is going to be algorithms that are polyfunctions of in value n, algorithms that are pseudo polytime is algorithms that are polyfunctions of the numeric value of input. Okay, algorithms are polynomial functions of the input value and numeric value of input. Numeric value of input n. Okay, cool. Makes sense. And let's see if I go to 3. Pseudo polytime algo for knapsack. Brampton which mundarata. Chotto I desu ka? Dare desu ka? We'll maybe take a tiny bit break after this, just to relax, stretch our brain muscles a bit. Because then we just got to go through the MDP questions, right? And then I can just do the last unit, which is simplex and shit, which is arguably easier because I've recently just given an exam on it, so it should be easier, I guess. Hoping it is easier. Honestly, I am just hoping that it is easier. Brampton which mundaranda. Bro, this shit's too crazy, bro. Like this. Usually it's good, honestly, but the amount of studying that I've put into this shit, bro, is crazy, dog. Okay. Brancham which mundaranda. My first Q sheet was not very clean, honestly. Just like random ass divisions and shiz like that, dog. Hey yo, Brampton which mundaranda. So honestly, dog. Yeah, there's some bullshit ass base case shit like that, dog. Yeah, sure, we got like P-TAS and FP-TAS shit like that, dog. Oh, hell nah, dog. Man, oh man, this is a pretty gnarly PDF. What is this PDF? Oh my god, MDP, bro. Fucking hate MDP. Come on, bro. Why are you doing that to me, bro? I really start it, bro. Markovian property. Yeah, that's some Markovian shit, alright. Brampton, Wichamund, Arenda. Okay, let's lock in. Let's focus. Okay, so we have pseudo polynomial time algorithm. We assume that our budget is small. That budget is polynomial in n. All SI are small. Then there is an algorithm that is big O of NP. Okay, let's note this one down. Okay, so algo 1. Okay, we are saying assume B is small, B equals poly of n. All SI are small. Then algo runtime is big O of NB, right? Base case is just M of base is hold on, how does this render? Oh, this does not render it as a nested list. Okay, fine. ओके देखते हैं, फिर देखते हैं दोस्तों क्या होता है. V0 if V0 if W is greater than S0. Let me see. Algorithm 1 says else 0. Okay. And inductive step is M of let's see, hold on. Okay, M of IW, some weight, Brampton, Wichamunda, and max of these two, right? It's gonna be like a max of M of I minus 1 plus W or Vi plus M of so I don't understand this at all, honestly. Okay, so and answer at okay, and I'll just say answer is at mn minus 1 and b. So we kind of gotta point it out at where the answer is existing at. TC equals space complexity equals okay, so okay. Brampton, which Mundarenda. Oh shit, I do need to do my flashcards. Let me do my flashcards real quick. Let me do my decks. I'll just do Golang study today. Array syntax is just where my array equals square brackets with some size and some int and some empty braces maybe. Sure, sure. How to initialize a struct variable and how to access the struct value. So you can just do type my structs. Okay, hold on. So let me just do 1149. Let me add a marker real quick, you know. Finishing flashcard quota of the day. Okay, anyways, how to initialize a struct variable. A struct variable can be defined as like type my struct and then in curly braces like name, field name type, and it's initialized as where my struct equals my struct curly braces name colon field 1 colon value, field 2 colon value, commas between each, and then to access value is just like my struct dot field 1, my struct dot field 2 or something. Cool, easy. Loop to get index an item, so it's just uh, for index comma value in range colon equals something. I forgot the loop syntax. Wait, hold on. I know it's like for index comma value colon equals range of my slice and this. Perfect, easy. Write a function that returns multiple values. So like func, cool func, and return value say float and float an int. You can just do return 0 and 0.5 and 1. That's how you can do it. Cool. This is easy. How to use weight groups? Okay, so you import sync, you do var weight group equals sync dot weight groups. You do weight groups dot add 2, and you just do for when you are trying to start a weight group, you can just do like when you're done with the coroutine, you can just do like weight group dot done, and it sends its now count back, and then you can just do something of that sort. Okay, weight group equals sync dot wg. So weight group dot add, you just add 1, and you just do weight group dot weight. Before exiting, it should be one thread before exiting. Okay, you aggregate add chain, right? I just did oopsie by doing ag. It should just be add. Close. ठीक है, so add हो गया. Wait, and in some blocking call, you just do done, and done के बाद. Okay, so at the end you need to add wait. That's important. Hard बोलूँगा. How to create a list of struct in Golang? You can just do var my struct list equals like square brackets type I think that's how it should be done. Oh, but you need to do make. Okay, you fucking need to do make hard. What is the right? Is this is the right declaration of maps in Golang? Where user data? Okay, now this is the declaration of its type. In order to declare an empty map, you need to do where user data equals make map string, and then some values like some size 0 maybe. Cool, easy. How to print a variable value? To print a variable value, you just need to do fmt.printf percentage v comma variable. That makes sense too. Creating an empty map in Golang where my map equals make map square brackets key data type, let's say string, followed by value data type, say int comma 0 maybe, which is like how perfect. Golang list of maps is just gonna be, oh my god, dog. Bro, shut the fuck up, bro. Okay, so for a list you need to do like make and second argument which makes it 0. You can just do where list maps equals make square brackets map square brackets again data type of the key inside the square brackets, say string. It's followed by that is the value, say int and comma 0. Okay, easy. How to define slices versus array? In slices, you just do not define the number. So if you want to define an array, you can just do where my array equals square brackets with 5 int, and you can just do curly braces and just define leave empty so on. And in terms of slices, it can just be like where my slice equals square brackets without any number int empty. Oh my god, this also is an option. Okay, hard बोलूँगा इसको. What does go mod init name do? It creates a module by the name of name, and everything can be imported by that module name. Okay. Here's a repository, plan to publish a module. Okay, cool. App name, cool. Easy. Syncing this shit. Let's see the stats. How many did I review? I did 12 reviews, which is good enough, I guess. Cool. So I'm gonna add it to my notes. 11:56 p.m. Finished going through 12 flashcards. Back to our grind, I guess. Sure, I don't think it's a good. Ow. Okay, now we go to algo 2, which is this. All values are small, so algo 2 is like I'll just call this like algo 1. Algo 2 is assume all values are small. All vi less than equal to say v max. Come on, dog. That's when this algorithm comes into picture, and we are saying that my base case is gonna be this shit. The base case is exercise, left as an exercise. Okay, I'm just gonna be like M complexity. Do they have like a n square v max? So save. So let's just see this. That's more time complexity. Okay, cool. Now let's see what do we do next. What do we do next? uh, Live drawing shared. Draw chat. Agree. Create new whiteboard. Sure, sure. Copying this link to my chat. I'm gonna give it a try, maybe. Let's see. Let's see. Let's see if this works, okay? We gotta check it out. Okay. 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 Safari, maybe. Draw chat. I don't know. Agree. There's another dude in here. Oh, there it is. There it is, bro. Oh wow, this is like a huge fucking canvas, dog. I'm just gonna keep it like horizontal like this because I just wanna be like, I just wanna open a like Safari like this, properly like this. I agree. Yeah. Yeah, that's okay, I guess. Cool. Cool. So I can just like maybe like, can I not zoom in, bro? Oh no, bro. I wanna zoom in now. Nah, dog. How do I zoom in? No, this just zooms. What the Sigma, bro? It's so annoying, bro. Oh. Shut up, dog. Yeah, move the viewport maybe somewhere over here. Something like this could be the viewport. I could zoom in a bit more, you know. Yeah, this looks good. And now if I say, yeah, whatever, dude. Okay, hold on. So, um, where's the fucking eraser, bro? Okay, there's the eraser. Okay, perfect. Now, let's see. Cool. So, I'm gonna be like, okay, start here. Then me take an eraser and then just get rid of the rest of these things. Cool. And now I'm gonna just like charge my shit. Real estate works, I guess. We'll get to that soon. Oh my god, dog. Oh my god, bro. Ah, fucking hell, bro. Why am I moaning, one might ask? That's because I'm just in. That's because I'm hustling. Okay, anyways, this we'll use in a bit for our further studies. Maybe. But yeah, for now we'll just figure out the algorithm. So n square v max is the one. Cool. And cool. Okay, so sure. Induction step is just this m of sure iv equals like min total knapsack size that suffices to. Okay, hold on. So we define table. Let's just say table structure. We are saying that it's min total knapsack size that suffices to get exactly value v using subset of jobs, some subset of jobs 0 I, some subset of 0 I. Okay. Then I'm saying that m of iv equals infinite if v not achievable using subset of subset of jobs this. So I'm saying that okay, MIV is min total knapsack size that suffices to get exactly value v using the subset of jobs 0 to I. I is okay, one of the argument, v is the value, min value. If it's infinite if it's not achievable. Okay, got it. Cool. Now we'll say base case, right? We'll say base case is gonna be like m of 0 v is gonna be equal to some 0 if v equals 0, else infinite if v greater than 0, right? That's how it will be. And m of I0 is 0. That's another base case. Inductive step is, that's going to be the base case. Inductive step is just this min thing. Inductive step is min of m of I minus 1v si plus m of I minus 1 comma v minus vi. What is v? Okay, if we create, okay, if for that particular, whatever, then we have to go through all these then. If v greater than equal to vi then, okay. Hold on, so complexity and okay, fine, sure, cool. Inductor step, sure. Answer is max. Okay, v max of v such that mn minus 1 v is less than equal to my b. That's my answer, I guess. Okay, got it. Got it. See this draft, bro. Okay, so 3 maybe. Let's see. PTAS versus FPTAS. Okay, so okay, sure, I'll just do this maybe. FPTAS is fully polytime approx scheme one minus say epsilon approx. What does it mean? Fully polytime approx scheme. Okay. Scheme approximation approximation that is poly in input size and 1 epsilon, 1 by epsilon. Okay, there's a 1 minus epsilon approximation that is poly in input size and 1 by epsilon. Okay, got it. And in the same vein, PTAS are just the simple poly time approximation schemes. So we assume that that epsilon is a constant, then you get a polytime algo that is polytime algo that is n to the power 1 by epsilon, right? To the power, okay, that's a crazy equation to render, not gonna lie. n to the power 1 by epsilon to the power 1 by epsilon. Crazy dog. Save as draft, please. What the sigma, bro? Did I break it or something? Okay. Okay. N to the power this to the power this. Maybe this would work. Okay. Maybe this. Okay, cool. So p task versus f p task हो गया. So like p task is not necessarily f p task is polynomial in n but not necessarily in 1 by epsilon, and but like f p task is like polynomial in n plus 1 by n p task. Okay, cool. And then okay, cool. Knapsack polytime algorithm, right? Okay, no, so not FP task algo. So we're saying theorem, an algorithm that value greater than equal to say 1 minus epsilon, this 1 minus epsilon optimization has optimization and has time bigger of n cube by epsilon. Okay, so okay, got it. So that's some guarantee that we're doing. Okay. 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 Okay, so I'm just gonna go through these FP-TAS algorithms, maybe. You know. Come on, dog. 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 Okay, is this the only thing remaining for this one PDF? This is just observation, okay. Okay. Algos value is greater than 1 minus epsilon optimization. Okay. ठीक है. भाई साहब थक गया हूँ भाई मैं तो मैड थक गया. supposed to take a break, but I didn't take a break, which is painful. Bruh. Bitches come and go, yeah. Bitches come and go. Bitches come and go. Bitches come and go. Go. Yo ho 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 ho. Yo ho 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 ho. Alright, dog. Alright, dog. Alright. Alright, dog. Alright, dog. Alright, dog. Hold on. Alright, let's just finish this shit up and then we'll take a small break maybe. Maybe I can go to Grad Algos Tech and I can browse Nap. The FP task for knapsack, bro. How does it render here is my question. How does it render here is my question. Oh, come on, bro. Why is it math jacks here? I'm like, dog. Let's say this is drafts and see how it renders. Okay. Save this draft. Let's see how this renders here. Bro, what the Sigma? Bro, what the fuck? कुछ मैटर हो गया क्या भाई तुम्हारा? ओके, स्टेप वन स्केलिंग फैक्टर स्केल करो थीटा से ये ऐसा आइटम से। स्टेप टू ट्रांसफॉर्मेशन करा दो, ठीक है। एल्गोरिथम डीपी टू फाइंड एल्गोरिथम डीपी, ठीक है। ठीक है, इसमें लिखना पड़ेगा एल्गोरिथम टू, एल्गो टू अबव। नाउ आई गो हियर इट सेज ओके, ठीक है। एन क्यूब एप्सिलॉन हो गया इधर प्रूव व्हाट आई वांटेड एसेंशियली। ठीक है, अभी अभी अगर मैं रेंडर किया इसको तो परफेक्टली रेंडर भी हो रहा है, सही हो रहा है रेंडर, ठीक है। नाउ लेट्स सी ऑब्जर्वेशंस। Whatever algorithm 2 returns the same value up to k in optimal in original instance, total vi is less than total vi value. Okay, it's not, it's gonna be slightly suboptimal, sure. It can be at most optimal, but not gonna be more optimal than what is already optimal. Okay, fair. Whatever is true optimal, it's still a good solution for, okay, fair. So I'll just go here and say 24 p.m. This was a hard PDF, honestly. Finished PDF 12. Knapsack. FP task. FP task versus P task. Or some algos for knapsack using DP and small values of B and V, B or V, ठीक है। Now 12:25, we can take a tiny bit of a break, can we not? We can, right? Yeah, so let's take a tiny break. I will announce it on the page here. Time for a short break, yay! Come on, dog. So we do like a tiny bit of a break maybe. And let's see. Yay! Okay, what am I gonna do? I'm gonna improve my online presence, I believe. You know, just gotta, bro. You know, a man's just gotta do that. That's all a man gotta do, you know. Okay, saving this image. Maybe in other documents, maybe. Okay. Shitpost? No, not in shitpost. Okay, I can just put it in Twitter PFP funny. FP find. Cool, that's one. Not this actually. Let's see. Not this, not this. Not this, dog. Not this. Let's just go to the gram, maybe. Uh, bro, that's crazy. Nah, dog. Shut up, dog. Yeah, we just gotta get that one picture, dog. That one picture, dog. We just need the one picture, dog. Okay, I think this is the one. Nah, this. Let's inspect this shit, okay? I got better ideas, honestly. I got better ideas, dog. Yeah, let's just do this in my documents, maybe. Okay, that should be done. Yeah, that should be done, I guess. That should be good enough. We'll close this sheet now. Let's see. Oh my god, dog. Oh, come on, bro. Maybe I could just go to my drive. Because the picture should be somewhere, right? Type maybe photos and images. Yeah, I don't need this. Nah, that's like a random ass. Okay, this is an important picture, I would say. Yeah, yeah, save this, save this. Uh, yeah, whatever. DP1 maybe, whatever. Oh yeah, this is another one, I guess. This is like the full size one. Yeah, this we need. Yeah, save this. DP2 maybe. Yeah, save this please. Yeah, please. Thank you. Oh bro, I didn't know I had like such cool pictures, dog. I forgot that I used to make such cool artwork. Okay, okay. Sure, sure. Man, I had that was like a disastrous hairstyle. Damn, bro, that's crazy. I'm glad that shit ain't saved anywhere. Glad that shit ain't saved anywhere. Beautiful. Yeah, I'm glad. Okay, that's like stoned AF, bro. I was like stoned AF. Man, why are my eyes so red, bro? Uh, Hoodie SZN. Crazy dog. That's a slick aura. Okay, this is pretty cool. Come on, we got. I know we got more pictures, bro. I know we got more pictures, dog. I just know we got more pictures, dog. Like you can't be like. You just can't be like gaslighting me, bro. All I'm saying is, dog. I just know we got more pictures, dog. Yeah, I know we got some pictures, dog. Why do I have downloads open, bro? I don't want download. I want documents. I want to see my documents, bro. Um, where are my Twitter PFP funny folders? Yeah, there's a stoned thing. Dog, shut up, dog. What is this shit? Damn, Zam, dog. Nah, dog, come on, dog. I don't wanna see these like stupid ass pictures, bro. अरे क्या है इतना क्यों पोल्यूट कर दिया है भाई ये? Why are there these pictures, bro? I don't want these, bro. Okay, okay. This is maybe fine. There ain't you, dog. What do you mean, dog? There ain't you, dog. Hold on, dog. Oh, I see. What am I doing? You all might be asking me. I'm just like trying to find a replacement professional picture for my LinkedIn. That's what I'm looking for. Don't select anything, dude. Are you crazy? Was I in this, dog? I wasn't in this, dog. It's crazy. Wait, where was I? Why was I not in my sister's own wedding pictures? Like, I should have been there though. Anyways, life goes on, I guess. Sure, bro. It's crazy. Mom and dad were crying and shit. That's crazy, dog. Man, look at me. I'm like laughing in the background, dude. Like, I'm just like shamelessly laughing. crazy. I was feeling no shame. I mean, sure, I guess. I love it, bro. I love it, dog. That's just how it is. Oh yeah, this is me in the straw hat, which is awesome. I think this was like my peak moment. My sister's laughing, bro. It's supposed to be like an emotional moment, but she's laughing. That's beautiful, honestly. That means that she's marrying into like a fun family and so on. Oh man, I'm just still laughing, dude. That's crazy. That's crazy, dog. Come on, how many pictures are there, dude? Why is there so many, dog? Why are there so many, dog? Yeah, these are okay, I guess. Nah, that's crazy, dog. That's crazy, dog. Where am I? Dog, where was I not there though? I mean, that's honestly crazy. Why am I not there? Bro. Bro, what the Sigma, bro? What the sis? What the Sigma, bro? Skibbity Riz, bro. Oh, that's pretty much how it's gonna be then. Okay, got it. I get it. Okay, not bad, not bad, not bad, bro. Bro, why? There's so many pictures. And I'm just trying to find myself. Where do many cameras? I mean, it's great. That's great, honestly, that's great. Oh, I see myself. That's crazy. That's crazy. Not gonna lie, dog. I mean, is there no option to exclude these ones somehow? God, because these don't end, dog. Okay, I think we're nearing the end, I guess, because it's like time stamped and so on. Nah, that don't make sense. Sure, dog. Man, oh man, this is tiring. How to exclude this shit? Not this shit, I mean this one particular folder, that's just too much. I want a dog. Bro, come on, bro. Come on, bro. You gotta be better than this dog. Please, dog. I don't want this. I think we're finally ending it. Oh, we're going back in time. I see now. Bro, come on, bro. You know, how do I stop? Uh, hold on. No. Let's just go before 2022, maybe. Yeah. Is that when my sister got married? Oh my god, this is just. I'm gonna close this tab because it's just bad. Oh, actually, I know there is this Google Photos, right? Not now. Shut up. Oh, no thanks. Thank you. Oh my god, I didn't even know that I had so many pictures, dog. Dog, that's crazy. That's aura, dog. Okay, we gotta like. How do we fucking delete something? Yeah, whatever, bro. Got it, dog. Muito três, dog. Muito três, dog. Let's see. That's crazy, dog. Hey, shut up, dog. Shut up, dog. How are these the most um really, is that it, bro? Nah, bro. Yeah, let's just delete this shit, bro. Cause you know we don't roll like that, dog. We just don't roll like that, you know. You know me, bro. Nah, dog. Nah, we don't roll like that. We just don't roll like that. Oh my god, that's crazy. Oh my god, we was crazy. We was crazy. We was crazy. Nah, dog, that was aura, dog. Nah, that shit was hard as fuck, bro. No, no, hold on, bro. Hold on, bro. Nah, shut up, dog. Okay, this was fun, I guess. Nah, dog, why did I have random pictures like this? Dog, that's crazy. That shit goes hard as fuck, bro. Dog, come on. That shit is nasty, dog. That shit's nasty, dog. Hey, shut up, dog. Nah, hell nah, dog. They're crazy. I'm stoned right here, bro. Hey, where's this chair going, bro? Yeah, bro, this shit crazy. They go hard, bro. Yeah, dog, this shit go hard, bro. What am I even doing? What are you doing? What are you doing? Okay, anyways, just tired. I need to do the Markov decision process thing. But fine, I will do it in a bit. You don't see a problem with this one. The problem with this one is it's just randomly lopsided, which I don't get. Why is it lopsided like this? This is a bit let's what can we call it? This is a bit triggering for my OCD. Let's see. Let's try to fix this diagram maybe. You know. I'm gonna do that really quick. Oh my god, this is just barely holding. File share airdrop to Shiv's iPad. Perfect, that's what I need. Okay, cool. Are there options to do aspect ratios or something? Square, freeform, original. Yeah, this looks pretty good, I guess. Yeah, this looks good, I guess, right? Done. Yeah. Now, the thing is, the problem with this image particularly is right that this. Hold on. Shut up, dude. Um. Hey, shut up, dude. Okay. Now just distort this a bit. No. Right. No. Okay, done. Just say done. Hold on, we'll just try once more. Hold on. Yeah, cool. I guess that's decent enough. I guess. Let's see if there's anything else here. There's nothing too crazy here. Hold on, dog. Hold on, dog. Okay, cool. Now, yeah, PNG, I guess. Cool. Ooh. Nah, bro. Okay. Okay, I think this is pretty good. Like, um, bro, 8. That's crazy, dog. Okay, okay, okay. Hold on. Okay, I guess this is decent enough. Okay, dog. That's crazy. Not gonna lie, dog. Bro, what the Sigma? Okay, dog. Come on, dog. Let's give it a try, dog. Does this work out or something? Nah, dog. This fucking looks like come on, dog. Come on, dog. That's crazy. That's crazy. That's crazy, dog. That's crazy, dog. Okay, cool. So let's see. I did take some break, honestly, didn't I? Where was I though? Let's see. 12:24, 117. I'm just gonna take like an hour, like for a few more minutes, like 10 more minutes maybe. Anyways, let's see. Okay. this is what we have, okay. Hey, yo, come on, dog. Wait, hold on. Okay, hold on. I gotta do some control, I guess. Okay. So this is one, okay. This is just one of these. Okay. When I do this, bro, what the sigma? Nah, screw this. Hold on. So Okay. Hmm. Okay, hold on. So, hmm. Let's get rid of this thing maybe. I mean, bro, I'm trying to like figure it out though. Hold on. Okay, I think that's good enough. Why is it not centered, one might ask? Sure. Why ain't it centered? That's just how we roll. That's just how we roll, dog. Yeah, pretty good. Mm-hmm. 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 Okay, okay, okay. Okay, girl. Security, security. Okay, girl. Bro, come on, bro. Why is this not very well centered? I'm gonna go to POI. Okay. Does it seem in the middle? I think so, yep. Actually, I'll just say cancel this. Yeah, this is good enough, I guess. Fuck it. Currently, a master's student in Georgia Tech Engineering. Okay. Okay. Cool. Okay. Cool, 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 cool. Okay, cool. I'm back now. So, let's see. Break over. Yay. Whatever, bro. Whatever, bro. I'm just tired. Too tired, bro. I know I should be like more focused, I guess, but whatever, bro. Whatever, bro. Anyways, let's see. Uh, shouldn't this be AM, bro? Lamau. Okay, cool. Man, I absolutely am hating this because this is just too much effort, too much pain, macha. Now we gotta do MDP basically. That's the problem, right? Okay, what is it that is causing me the discomfort is what I'm thinking, right? Like, one is sure. I'll be pasting this bullshit into uh, my notes app could be one of the reasons why this is so uh, non-pleasurous or whatever pleasure. What am I saying? मेरा grammar भी हग रहा है भाई. चलो कोई दिक्कत नहीं, वो तो हगता रहता है ऐसे, ग्रामर भी ठीक है. Interesting. ओके, सो मार्कअप डिसीजन प्रोसेस पे हम काम कर रहे हैं दोस्तों। मार्कअप डिसीजन प्रोसेस पे हम काम कर रहे हैं दोस्तों। ओके, कूल। ओके। ओके, श्योर श्योर श्योर। Sure, sure. Markov decision process, okay. Okay, cool. ठीक है. Now let's go through this. You have stochastic probabilities. If an algorithm takes an action, the output is uncertain. Okay, sure. That an environment at state 1 and state at time t plus 1, and there's an action that will be taken at time t, and based on that you will have the environment at some different time, different state. Finite state space S. Okay. Oh भाई क्रेजी हो गया, क्रेजी हो गया भाई. Finite state spaces S, finite action spaces A. Start state S belongs to S. Transition probability, there are some transition probabilities at P A S S bar for A that belongs to A. S S bar belongs to S. Okay, fine, sure, whatever. Sure, there's some inputs that you are getting. The question is, do I need to put any of these Markov decision process things in here? Like bro. Okay, actually, you know what? Like, I'm just going through this definition. There's some definition for policy. Tells us that action A, T, belongs to some action space to take that step at T. Okay. Okay, finite state action space A. ठीक है. There's some action space. There's a ref. Okay. There's a goal somewhere. An algorithm policy tells us what action A that belongs to A to take at step T. ठीक है. Denote S by T state of policy. Okay, at time step T. Fine, sure, sure, sure. We have this example. Okay, I farted. Okay. Okay, I think the way I should be doing this is just I'm gonna just add this to my cheat sheet. I'm just gonna add this to my blog dog. You know, and then I'm gonna go through like an example maybe. You know, Markov decision process MDP. It's basically the definition is finite state space S, finite action space A, start state S1 belongs to your entire state space S. Cool. That's what we know so far. S1 belongs to S, and then there are some transition probabilities. Transition probabilities. These are given by, say, probability A, S to S bar maybe. The probability of transition from state S to some S bar for for some action in A S and S comma S bar in the state space. Okay. We should also note that the sum. What am I doing? What am I doing, bro? The sum of probabilities over all states, say S bar in S, PA SS bar is equal to 1. Cool. So if I just reload this should be right. Cool. That's 1. The input that we are getting is of the order some S, like some state space square times your action space ka size. Okay, so the input is of the size twice of the states, like the square of the state space. Why? Because if you have unique state S, like if you have a state set of size S, then any state can technically transition to any other state. So that's why you get squared possibilities into action, because you'll have some action that you'll take, and then there will be like some rewards which will be, say, defined as some RA. There will be some reward for every state that you are in. Math BB. So your rewards are going to be real valued rewards. You won't have imaginary rewards. Fair, makes sense. Imaginary rewards nahi hai, real valued rewards hai. Fine. Now your goal is given time horizon T. Okay. Goal is given time horizon T. Design an algorithm or policy. Design an algorithm, or you could call it policy, that plays actions to maximize the total expected reward. Okay, that plays actions to maximize the math BB E text total reward. I think this is how it should be rendered in LaTeX. Yeah, okay. Just so that people understand what I'm looking at, maybe. I'm just gonna go here, I'm gonna paste it here. So I'm taking all my notes and just noting them down here. So you can see it here that all the notes that I am taking are over here like this. So anyways, that's just what I was saying. Cool. Okay, that's what I know now. Okay, and what is the definition of a policy, right? Policy definition. What's a policy definition? An algorithm policy pi tells us what action sure, I know that, thank you. Sure, I guess. Pi an algorithm policy pi tells us what action uh, which is defined as t and some pi. How is an action defined again? Let's see. Action at time step t for the given policy. Okay, action belongs to some policy and okay, cool. In your action set to take, okay, algorithm policy pi tells us what action at time step t to take. Okay, to take at time t, take at, it's not time, you can just call it step maybe. Okay, cool. Denote state of policy pi at step t as hey yo, why am I getting another notification? Dog, come on dog. Thank you, LinkedIn. This was just me. Ow. Dude, come on, dude. Thank you. macOS, yeah, that's me. Anyways. Okay, so a state also belongs to a policy, so it's just gonna be S of pi by t underscore t. So this is just gonna cool. This is just pretty good rendering, I guess. Cool. Sure, that's okay, I guess. And now you have some gold that we need to maximize. That's fine, I guess. That's okay. Don't do that, dog. Don't do that, dog. Goal is to maximize this. Let's do this real quick. Oh, shut up, dog. Come on, dog. So that's the goal. I get it. And this is like the TP algorithm, I guess. Mm-hmm. Let's see. So this is anyways gonna be on my cheat sheet, I think. I don't think I need to be so worried about this, right? Convert this to latex, maybe I can do that. Okay, cool. So I'm just gonna go here real quick. 6 is gonna be just this. Maybe same with this draft. Oh my god, dog. Why is this not working? What is your problem? Oof, what's the hold up, bro? Goal is like given time horizon T, you need to maximize this bad boy. Okay, I get it. And like maybe point 0.7 would just be this, right? What happens if I save this? Ow, that does not look good at all. Do it. Do it, do it, do it, do it. Use dollar syntax instead, please. Instead of let's see if this does a good job at it. Habibi George Bush. Come on, dogs. Come on, my dogs. You know how it is, dogs. Save this shit, bro. What the fuck? What the Sigma? What the Sigma? Why is this not working, bro? Wait, some rendering is fucked here. I guess this is because of this, maybe? Maybe like this bit makes it better. Okay, it's somewhat okay-ish, I would say. Okay, sure. Okay, got it. Okay, let's we just understand this a real quick. I need to go through some examples for this, I guess. I'm hoping that they do that. But we know that for some policy, this is the reward of the step. Sure. Reward of T minus 1 steps are these. So you're saying that you can just use uh, dynamic programming and just make this like a max of all actions over reward A plus summation of some probabilities times probability time this, right? Okay, got it. The space is st. Did I cover this? I did. Okay, space is st. A square t. Cool. Got it. Got it. Cool. So let's see. 2:07 a.m. finished PDF 13. I'm just gonna say that this was just MDP stuff and DP equation for value iteration. I know the final exam ain't gonna be this complicated, honestly. This was this was told to us much earlier, so it's fine. Now, okay, this is pretty decent, I guess. Cool, let's open the next set of papers, maybe. Cool, we gotta go through simplex now. Copy link. Yeah, I'll just open it in here, I guess. Simplex. Actually, I'll just do type notes on simplex because these are like easier to read. We'll go through these maybe later on. Cool. Copy link. Okay, let's see. Simplex, gradient descent. These are like very easy things. Like these are like, this is which one? Okay, this is gradient descent 2, I believe. Yeah, this is like an easy chapter, I would say. We'll wrap this up real quick. Honestly, I know that for sure, dog. Okay, hold on. Maybe if I open this, what happens if I do this? Is a proof. We don't need to even look at the proof, honestly. I know that for sure. Fine grained complexity, maybe. Sure. Sure. Could go for fine grained complexity. Okay. Triangle detection we'll do next, maybe. See, this part is not gonna be too bad, I guess. Yeah, the set and OV is gonna be the complicated part, I guess. Okay, so these are all the notes. Yeah, this part's gonna be the harder ones, I guess, like from this one onwards. It's gonna get significantly tougher, I believe. Yeah, I don't know. I have no study strategy for this. But okay, let's see. OV is essentially 19. But I think we can just go from 14th to 18th right now, because that's also pretty good. 14th to 19th maybe I could do. And this part, the remaining last part on set OV and so on. Okay, let's maybe make it into a plan, I guess. Finish going through PDFs 40 to 19, start of 19 only. Okay, so I guess that's how it is. And yeah, let's maybe add some more things to the plan. Review MDP example in the exam, I guess. Wokies. Wokie dokies. Cool, let's go through simplex maybe. I wouldn't believe. My god, this one's gonna be like a very lengthy one, I would say. What is the time? It's 2, 2 to 3, 3 to 4, 4 to 5. So we have 3 hours to maybe recap. I don't know if you can finish it in 3 hours. We can give it a try though. 3 hours to go through this shit, and then we can spend the entire day tomorrow just going through 19th to 24th and previous exams maybe. 19 to 24 and previous exams, that's all we can do then. Because everything after this is just too fucking crazy. I don't even know if we have the time to go through this. We can't do a revision, right? We have to at any cost finish our revision by tonight, right? So okay, let's see what all do I have so far here. Okay, so we have DPs and so on, I guess. So the thing is, I'm gonna be like speed run through this because you have studied this most recently, so don't worry too much about this one. Okay, cool. Simplex recap. I could do the blog thing. Amacha. But I think I'm just gonna skip because I wouldn't believe. Okay, so we have the following standard of LP firm. This is your max of CTAX less than equal to B, which is fair. We're gonna follow the algorithm solve these. The high level algorithm idea is this. You assume that we have some corner. We check all edges incident to the corner. Sure, fair. Do I have this somewhere? Check all edges incident to the corner. If one of them is improving, C transpose X, moving along that edge to the next corner. This is our objective, so if anything gives you better performance, sure, move along that corner, else return the corner X. Our goal in this lecture is to formalize the intuitive algorithm. Why can't there be a local optimum? Again, there can't be a local optimum because this is a connect set. We don't need to go through this. How does this not boil down to a graph problem? The input is generally a bunch of constraints, so it's not clear what the edges are, which is why you can't efficiently construct a graph. Okay, got it. Okay, cool. Makes sense. Is a graph problem? They could ask, is this a graph problem? And I would just say no. In moving from one corner to another, how should we choose among multiple edges that increase the objective value? In moving from one corner to another, how should we choose among multiple edges that increase the objective value? Hold on, thinking. Did I believe? Let me go. Let me go. I won't give up, nah, nah, nah. I won't give up, nah, nah, nah. Let me. Okay, cool. Okay. Anyways, bro. Okay, a bunch of constraints was not clear what edges are, which is why we can't efficiently construct the entire graph given just the constraints code. Uh, how should we choose along multiple edges that increase greedily? You can just choose greedily. It's still an open problem, okay. Popular choice is too greedy, but there are other examples that you can read longer path. Okay, sure. What is a vertex? Vertex is any point which is going to be a unique solution to some D constraints, uh, where it's feasible everywhere, like ax less than b, x is feasible for all constraints, and D constraints it satisfies tightly. We can also call a set of linear independent constraints that we can also call a set of D linear independent constraints, then define a corner a feasible basis. A feasible basis, okay, fair. This is because AB is basis for RD, and because solution ABX equals BB is a feasible point of linear program AX less than equal to B. Sure, sure, sure. Got the set of, okay, sure. Uh, this is a feasible basis का definition है. What happens when we specify less than D constraint D minus K? We just get some K dimensional face of the polygon. What happens if we may consider some linearly dependent constraints and D constraints? You won't find a unique solution, you won't find a corner. To run simplex, we move from corner to corner. How do we get the first corner? Okay, that's like some very complicated shit. I don't know how to get first corner. I don't think they're gonna ask this, but whatever. To specify corner, we must specify D constraints of linear program to be tight. What if the okay, less than, it's unbounded? It's unbounded. What if the linear program itself has less than D constraints? It's okay. It's about the feasible. Okay, fine. What is an edge? Sure. Cool. Edge is where the symmetric difference between two set of constraints is 2. Cool. You just, okay, fair. Have I given the definition of edge somewhere over here? Yeah, two vertices x and x bar are x prime are connected by an edge if there are feasible bases b and b dash that differ by one element. Okay, got it. That asymmetric difference is 2. Sure. All points on an edge x and x bar satisfy AB excluding I equals something 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 BB excluding I. Sure, fair. Okay, how do we get all edges incident to a corner? Simplex algorithm, it must check which edges could improve CX. Okay, so it checks for feasible basis. Oh, okay, so it just keeps swapping out various corners and edges, I guess. How do we get the direction of an edge? How do you get the direction of an edge? You just do x minus x bar, you solve it, and you get something like AB inverse EI epsilon. Yeah, intuition. If we perturb, okay, previously said we need the direction to figure out. Okay, we perturb a face. Cool. And this is not the only edge, this is also going to be moving, and this is also going to be moving fine. So you do this operation over here. The direction of an edge can be computed by doing this. So EI is going to be like the direction in which EI is going to be the ith constraint that you are going to like swap out in the direction in which you're going to move. But now you got to know how, by what quantity you should move. Okay, sure. Oh yeah, this is like an important result, that Cx Tx bar should be greater than Ctx. And in general, picking the correct edge means that your C transpose AB inverse I is less than 0. Fair. This part basically, got it. How far can we move? How far can we move, bro? To move far, you can just do x bar equals x minus AB inverse something something something. And yeah, to move far, you can just do this stupid ass thing. This is just swapping in x bar. You're just adding x bar here, and this needs to be feasible, so you just rearrange this, and this main thing means the first constraint that you hit, right? This is gonna be the first constraint that you hit. Cool, this makes sense to me. The algorithm is simple. Find I where C transpose AB inverse. Okay, if there exists such an I, you calculate lambda. This is going to be the distance by which you need to move, the quantity by which you need to move, and you just do AB inverse times this. This is the perturbation and so on. Okay, sure, cool. If okay, so if you see any direction, if you see that, because it's a convex set, if you find like an optimal value where there is no other improvement possible in any other direction of the edge, then it means that that is going to be the most optimal value. So C transpose AB inverse I. Okay, sure, fair, makes sense. Stalling could be when your lambda is 0, or when you have more than D edges constraints incident on a vertex, like edges incident on a vertex, then you are just like moving around the same vertex. So that's called fine. That's called a degenerate corner. Fine. This makes sense. Sure. This is cool. A polytope has at most T feasible basis. So T is less than equal to ND. Okay, so have I written this somewhere? Runtime without cycling almost T iteration squared. Okay, got it. Sure, got it. Okay, so each iteration cost bigger of D square. NNZ is like number of non-zero entries in A. Big of D square equals compute A inverse. Okay, NNZ this. Sure, Sherwin Morrison and so on. Fair. This is good. We'll finish this. Cool. So 229 is what it took to finish 229 M14. Cool. What did it go to? Simplex algo details. Cool. 15. So 15 has like two parts. It's like gradient descent 1 and 2. So we'll just quickly go through this shit. Sure, this is basically the definition of a convex function. Like if there is some t that is between 0 and 1, then the convex function is f t x plus 1 minus t y should be less than. So basically the LHS is like the lower bound, RHS is the upper bound for the LHS basically. Like this is like the straight line between 2 points, whereas this is like the actually follows the function. Given convex lambda, given convex function, we want to find minimum maximum. Gradient is just derivative is going to be the direction of the gradient steepest t ascent. Delta fx I is fine. Negative of the gradient is steepest. Negative of the gradient is steepest descent. Typically we want to go to minima, so we're going to go to the steepest descent. Eta is going to be like some sort of step size that you get, right? And eta is typically like eta step size. The step is usually like eta times delta f of x t, nabla f of x t is gradient. Fair. A smooth function is if the second derivative exists and it's like upper bounded by some value L for all x and y, you sorted. That's your L smooth. Yeah, this is like the definition for L smooth, and this theorem that okay, king corner undefined gradient continuous at some point, maybe. Sure. I couldn't believe. Okay, sorry, my bad, bro. My bad, baby. My bad, baby. You don't have to be so mad at me. So I think I've written down these identities. Like this is like if f is L smooth and convex, then the step size is like at most 1 by uh, L. Then how far away. This essentially tells you how far away are we from the optimal. It's like x naught minus x bar norm by 2 eta d. Sure, fair. And example application, sure, just like whatever, right? This is fine. This I know. This is like I've done it very recently. So 15.1 and 15.2. Never let you go. Never let you go. Don't you give up. Nah, nah, nah. Won't you give up? Nah, nah. Okay, sorry, my bad, bro. My bad, bro. My bad, bro. So, say 2:33 a.m. finished point one. Okay, let's go to PDF 15.2. This is 15.2 for sure. So this is what we covered. And for L smooth, we have this one particular lemma, which is like a very important lemma, and you can just keep using it anywhere. You don't need to go do this integral thing. That's bullshit. Sure. Delta less than equal to this. Sure. Eta equals 1 by L. Sure, easy peasy, lemon squeezy. Eta by 2 is fine, I guess. Theorem f of t minus fx star 2 eta t, sure. Okay, now let's see. You just do this proof. This proof is fine. The only thing that you do in this proof is the interesting thing that you do in this proof usually is okay. Never let you go. Never let you go. Sure. I know these proofs. These are like pretty trivial proofs, honestly. I'm okay. I'm okay. I'm just gonna be like skipping through these because I've recently studied these. 2:35 a.m. Finish PDF 15.2. I'll just say coverage was L smooth proofs and lemmas. 16th now. So let's go to 16th, which is gradient descent 2. So what happens if your function in general does not have a derivative, like for example the max function? So you are saying that if its derivative exists and it's upper bounded by some value L for all values and it's sorted and you're done, you're good. Yeah, this is fine. This is just an example. And it's called an L Lipschitz. This is the same sort of thing, I guess. And L Lipschitz just has like two. I remember L Lipschitz just has like these two. Identities somewhere. Yeah, this is the theorem that you just have. I think that's like the only thing that you have, like the summation of all function values by all time, but like the average function value minus the goal is gonna be less than, like this term stays constant. You just have like eta L square by 2 as an extra term now, and this is again the same. It's just like same thing. The first is stronger than the second, it seems. And yeah, this is pretty good, like the function property and the iterations. Yeah, pretty good. This is just, I think, some analysis. We don't need to get into this. Stochastic gradient descent. What about stochastic gradient descent, dog? When you do not have a gradient, you only have some random GT with some expectation, which is gonna be like expectation is gonna be the gradient, sure, and GT is like less than some L. Then gradient descent still works with some guarantees as regular gradient descent. Cool. Stochastic gradient descent still works, it seems. Cool. So it took me what? Fine grained complexity theory. Sure, we'll go to this. This is gonna be a bit tougher, I guess. But anyways, uh, L Lipschitz and stochastic gradient descent. Cool. 17 dog. Let's see. I just did 2:38 a.m. Finished PDF 16 by 2:38. Now let's do one thing. Like one important thing that we usually need to do. Okay, cool. Now let's do one thing. Okay. I know there are some proofs that we need to work on. I'm gonna just open up my problem set. 6, I guess. Yeah, let's open up problem set 6, okay? Okay, let's do this. So, typically, these are like some problem sets, I would say. The 19th question is easy, I would say, but hold on. Did I open up the solution? I don't want the solution, I just want to figure out myself. Hold on, not solutions, just problem sets. 6, I guess, sure. Wouldn't believe. Okay, so we're gonna skip 19, but we're gonna start with 20th, for example. Dog, what the sigma? Hold on. What does it mean? Is it in? Oh, it's of course it was here, right? Okay, cool. So let's try this. So the first is this. Okay, so first is what? Oh, shut up, dude. Okay, cool. So we have to show f of x t plus 1 is f of xt minus eta 2 okay, cool. This is what we have to basically show right now. I'll just like switch to this one. Cool. So this is where we are at right now. This is what we need to prove. So let's see. Okay. Okay. So we know a few lemmas. We know this lemma that goes something like f of y minus f of x plus what was that lemma, dog? Give me the cheat sheet, please. What was that lemma, bro? I know there's a lemma that says f of x plus gradient of f of x transpose, I know, y minus x. This one is less than equals L by 2 uh, y minus x. Cool. The square. I know this is like something that we have. This is the lemma that we have given in the class. We also know, we know that x of t plus 1 is just x of t uh, x of t minus 1 is x of t plus your minus your like step size. It's just gonna be like eta by, right, this is what we have. Say this is my y and say this is my x, right? Now what I'm saying is, right now what I'm saying is, if I plug this into the lemma above, right, if I plug this into the lemma above, that is this one. So I'm saying that f of xt plus 1 minus, and again note that this does not apply to uh, uh, this lemma holds true for convex as well as non-convex functions. So xt plus 1 minus uh, xt plus 1 minus x. Now notice uh, notice how this thing is just uh, this thing is just negative eta uh, delta f of xt, right? because of because of 1, right? And same with this is also negative f of xt. So if I now simplify this again, I'll just get f of x t plus 1 minus of notice that I have negative eta, and now I again have f of xt. This is less than L by 2. I can take eta out, but it will be squared. So I can do this. Now I can combine these two terms and write this as, hold on, I just need to like, this is how I can write it. So this becomes minus um, uh, minus of, let's see Uh, sure. Actually, I can just like rearrange this now. I can just move xt to the other side. I can just be like, okay, you just become f of xt here. Um, this was a minus, right? This minus and this minus became a plus, and when that went to the other uh, side, it became again a negative. So um, eta of this is what we have. Now on this side we'll also have something else. We have this thing which is plus L by 2 eta square. Now if you carefully observe, right, if you carefully observe this, you will notice that yeah, you will notice that uh, we know that eta is at most 1 by L, correct? Eta is at most 1 by L. So if I were to substitute that here, I could simplify the above equation as something of this sort. Eta plus just eta by 2. Cool. And now notice how this term and this term is common. So this is essentially f of x t plus 1 f of x t uh, f of x t um, plus times this is minus 1 plus half. This basically becomes a minus half, and then essentially you get to write your final solution as f of x t plus 1 is less than equal to f of x t minus and yeah, hence proved. So this is like a pretty simple proof, I would say. Like if we see this, this is what we wanted to essentially show at the start. Sure, I have definitely increasingly made my handwriting much bigger, but you get the idea. This is the required proof. Now we can try the next set of proofs, maybe. Let's see what is the next one. Okay. Next one says show that summation of t f of x k is less than 2 by okay. Okay, so this is what we have to prove. So I'll go back to my board here. Let's see, thinking. How does one prove this? We have some result over here which gives us some information about this. If I do rearrange things, they do seem pretty straightforward to me. Right? If I do rearrange things, uh, sure, sure. F of 0 to f of star, right? Okay, got it. Okay, so I can see that I can use uh, uh, using result from previous question, we can write using result from the previous question, we can write that for some okay, let's just say uh, let's just rearrange these terms, right? We can just write that f of xt, right, minus f of xt plus 1 uh, or hold on, I could just rub this thing and I could be like, okay, hold on, I could be like, if I move this term to the other side, I can be like, okay, delta f of xt square is less than f of xt minus f of xt plus 1, the whole thing 2 by eta. I'm just uh, rearranging, right? We just rearranged things. Cool. Now take a sum from t equals 0 to t equals t star, maybe. This would give you this, which is what you need on the LHS. And this is just saying, you are saying f of x0 minus f of x1 plus f of x1 minus f of x2, so on and so forth, minus at the end you're gonna be left with f of x star, and you can see that these terms cancel out, so at the end you're just left with tx equals, sorry, tk equals 0 yeah, you're just left with so hence proved. This one was like a pretty straightforward uh, question, honestly. Cool, so this is easy, this is proved. Cool. Let's see what's the next thing to prove. It's show. Next thing asks to show that the min of k from 0 to t is this f of xk is less than like the root of 2 by eta t. Okay, sure, let's go here. This is what we need to show now. Again, it's gonna be pretty straightforward. uh, we can just use the result that we had seen above, but we can just say that notice. Okay, we can just say notice that um, we're looking at some min value here, right? So notice that sum of uh, okay, so uh, we are saying sum of min is less than or equal to uh, sum of entire set basically, or set collection. This is basically a property, right? So I can, without loss of any generality, I can claim, I can rewrite the first proof that we had as, I can just write it as I can just write it as yeah, I can just say that, okay, God, I need like an eraser maybe just to make this cleaner. Come on, dude, shut up, dude. Cool. So I'm just saying uh, okay, so we don't need a k here. I don't want to use some k. I'll just use I. I'm just gonna say k min because it's smaller, right? That's what you're claiming. Right, this is what we are claiming, right? Now if this is what we are claiming, then you can simply say that, hey, you know um, what is it, uh, I can simply claim that, hey, you know what, this sum is just t times because it's just summing, so it's just t times this is what I can do. Now I can just divide both sides by t and take a square root and I get this. F of x star. You know what, I don't like the shabbiness, which is what we wanted to see, hence proved pretty decent, I guess. Sorry, I was not focusing on this. My bad, bro. My bad, bro. Cool. So this is also proved. Let's go to the next question, I guess. There are five sub questions here, but let's just quickly start solving them. It's pretty straightforward, I believe. But whatever, right? Would I believe? So this mu convex function is also pretty important, I would say. So let's see. Show that x t plus 1 minus x star square is equal to xt minus x star wow, this is some huge shit, bro. Whoa, what the fuck? Wow, okay, so I'm just going here now. And that's some crazy shit. Why is this so big, bro? What the sigma? Oh, what the fuck is this, bro? Okay. Mm-hmm. Wow, it's rendering painfully slowly. Okay. Anyways. Okay, I think this is straightforward. We know that uh, xt minus 1, xt plus 1 minus xt, some xt is typically equal to minus eta. This is what we know, right? And right, this is what we know. Say xt plus 1 equals x star. Say, assume it, okay? We also know this identity that u minus v plus, this is what we know. Again, this is like standard linear algebra shiz that we know. So what I can do now is I can just substitute this in this. So I'm basically getting LHS right away. Hold on, what am I doing? Is this what the proof asked? Xt plus 1 minus x star. Okay, sure, I guess. Okay, hold on. This won't work well, right? This won't work well, honestly. Thinking. Oh, okay, I get it. I think I need like an adjustment. You know, we definitely know this. This is fine. This result is still very relevant. Result is still very relevant. What I'm trying to do is, I'm trying to see if, okay, this is still this, right? So, okay, I see. I can say that my LHS, I'm just using xt equals xt minus eta I'm not getting rid of. Okay, so this is just xt plus 1, right? It's just from this one. Cool. So if this is what I have, and then I say rearrange this, and say I am gonna be like, okay, x uh, t minus x star, this is my u, minus say this is my v. God, look at that horrible v. This is my v. Then I can say, using this using 1, I can now say that I have x t minus x star square minus 2 into xt minus x star times minus of eta, so this basically becomes plus. Oh no, this doesn't become plus, my bad. So delta of xt, right? So sure, I guess. And at the end, you just have this plus eta square delta f of xt square, right? Hold on. So I made a boo-boo here. I was right. I just was not paying attention. This is right. Cool. And now let's see how far away are we from what we need. So this term we have, this term we have, this term we have. Yeah, sure, fair, makes sense. So now if I just rearrange these things, I can be like, okay, this is literally just expansion. To eta this was plus, my bad. Oh my god, dude. So yeah, hence proved. Cool. So this one is easy. I think this second section is pretty straightforward. I'm just gonna go through this and just gonna see if there are any obvious problems that we can do that could be hard. Delta f of x t, you just have to use this part in this one. It's pretty straightforward. For 3, you just have to use this identity. Do I have it in my cheat sheet though? I have it. Just gotta use this in the cheat sheet. Fair. Combining these 3, I can see why this works. Iteration part is also straightforward. It's trivial, so I'm gonna close this. So I just wanted to ensure that I'm able to do these proofs as easily as possible. I'm able to do these proofs. I'm pretty confident with my ability to do these proofs. So I'm just gonna end this session for the whiteboard. It's a pretty good whiteboard, honestly. It's a pretty good whiteboard. Okay, let's see. If we finish PDF 16. Oh, this one's like a tougher one, I guess. This is like a pretty complex problem statement, but let's do this, right? 3:12 a.m. finished doing practice proofs for gradient descent. Whatever, my bad, bro. My bad that my spellings ain't so good. Okay, sure. Find grain complexity. Let's see if there is anything important to cover in this one. So we have the OV problem, orthogonal vectors. It's just like you have two sets of vectors v1 and u1. If I asked if there is exists an orthogonal pair, it's a yes no question. OV conjecture is this. There exists no algorithm that is 2 n to the power. Yeah, there is no 2 to the power n to the power 2 minus e epsilon poly d algorithm for OV. Sure. I buy that. I do believe that there is no such algorithm that exists, which is why we are in this conundrum. Okay, I get the reduction fair. Uh, there is like explanation of a reduction. This is just like a theoretical proof. I don't think we need to worry about this. OV conjecture. Okay, so the closest pair, assuming OV conjecture, assuming something, conditional lower bound, right? Wait, I had this heuristic somewhere in my notebook where if someone says assuming something, you immediately do a particular type of reduction. Let me go find it real quick. Not this. Not this, my friend, not this. Let's see. I don't believe. Okay, let's think a bit about this. So, assuming something, there's a language to this. There's some language that basically tells you. Yeah, sure, whatever. Let's do this. So, if you're saying assuming OV conjecture, no problem can solve closest pair in this. Assuming OV conjecture is if there a problem A is being reduced to B. Assuming is कहीं भी आ गया तो वो A हो गया. A को हम reduce कर रहे हैं B को, right? We are saying कि OV closest pair. Okay, let's see. A reduces to B, sure. I get it. I get these. Hold on. Wait, let me just check the language for this exam once real quick. Not this, sorry. Not this. I don't believe. Hold on. I think it was in practice exam 2 or something, I guess. Now. Okay, so some heuristics that I had thought of is assuming OV conjecture बोले तो अगर if okay, here is what I have figured out. Okay, if someone says assuming a conjecture, someone says consuming a conjecture, then it's the outer shell. And OV conjectures has vectors as an input, assuming OV conjecture. So A is being reduced to B. A uses B, essentially. Assuming OV conjecture, we cannot find triangles in this time. So, okay. Assuming 3-sum. So 3-sum is going to be outside. And inside there's going to be non-negative. So assuming बोला तो it's going to be A. उसके अंदर B बोलना है. Right, 3-sum fair makes sense. Okay, got it. So let's go to the notes real quick. So when they say assuming OV conjecture, it means that we are trying to implement OV conjecture using this closest pair algorithm. Cool. Closest pair to use closest pair to solve OV. Okay. Reduce OV to closest pair. Sure. Our reduction is big O of ND time reduction. So sure, reduction should not be greater than this. This is how much time we spend in addition to calling this. So subquadratic reduction, if I'll go for B is big O of n to the power epsilon, then I'll go for A is ठीक है. There's some conjectures that say, okay, 3-sum, we say that 3-sum cannot be solved in subquadratic. The input to 3-sum are 3 sets, outputs are yes and no. Let's see. And there are some variations where 3 sets become 1 set. And like if you're given ABCs and you're said, okay, you know what, your given input is ABCs, but your reduction requires 1 set. Like B takes input only as once, S as an input. You can just do max things, and just if 1 set goes to ABC, you can do A, S, and to create duplicate copies, and C can just be like a negative. So A plus B equals minus C, for example. That could be 1. Cool. That there is all path shortest pairs. APSP के लिए इनपुट एक ग्राफ आता है और आउटपुट एक मैट्रिक्स आ जाता है. And this cannot be done in subquadratic. Then there is Boolean matrix multiplication, जिसके लिए इनपुट मैट्रिक्स आता है and output भी मैट्रिक्स आता है. So APSP is graph input output matrix. BMM is input matrix output matrix again. And this is also not possible in subquadratic. Fair, cool. So let's see GA final study 321. Let's see what did I do at 321. 3:21 AM. Finished APS. Okay, finished PDF 17. What was in 17? OV. Come on, dog. OV conjecture. Closest pair problem. Reductions. Other conjectures. Okay. So now we go to 18th. This is 18th triangle detection. Boolean matrix multiplication used to do triangle detection. So okay. So whenever someone asks you to do something from graph to matrix, right? If someone's ever asking you to do something from graph to a matrix, you immediately use an adjacency matrix, right? Okay, sure, दोस्तों. If someone's asking you to use a Boolean matrix, my bad, bro. My bad for burping, bro. But studying very hard, yaar. Hmm. So BMM is pretty straightforward. It's just like, okay, your input is like two matrices A, B, N cross N, and you just gotta tell if the output is like some matrix C, N by N, if there is like some non-zero entry somewhere. And typically, triangle detection, you can just say that okay, you do Boolean matrix multiplication. So assuming triangle detection, so ट्रायंगल डिटेक्शन को बुलियन मैट्रिक्स मल्टीप्लिकेशन को रिड्यूस करें हम, ठीक है, ऐसा उल्टा करें हम. सो हमने ये कर दिया, उल्टा साइड पर डायरेक्शन करना है. सो ओके, देयर आर टू थिंग्स. If you want to go from a graph to matrix, so Boolean matrix multiplication is actually a matrix. Matrix to graph के लिए हम tripartite graph use करते हैं. But if you want to go from triangle detection to matrix, like if we have a graph which is graph to matrix, if you want to do graph to matrix as in if you have a graph as in like if you have an adjacency matrix, and if our output is also a matrix, then we just use an adjacency matrix. If you want to go from matrix to graph, so we use a tripartite graph. So if you different triangles, okay, sure. This is like complicated shit, but the idea is that yes, we still can do it in subquadratic. The other way around is also possible. The most important things to remember here are the main ideas, that like what direction and triangle detection algos. Sure, let's see. This is pretty straightforward, I would say. 25 a.m. Finished. PDF 18. Now we gotta do like 19th. It's not gonna be too much, I guess. Search and verify. Sure, searching and verifying is pretty straightforward. Yeah, I don't believe. Oh shit. Hold on. Hold on, bro. Okay. Okay. Oh, my ass hurts so much right now just by sitting in one place. Okay, anyways, let's quickly do this. We are only gonna do some start parts of this, I guess. But yeah, this is like very reading heavy, I would say. Like, how many pages is this, dog? 5 pages, fine. Okay, not too bad, honestly. Yeah, my god. This crazy. This boy is crazy. This boy freaky. Sorry. Yeah, I don't believe. I think we could do some examples maybe. I still am trying to figure out like a good strategy to do the final syllabus thing. I don't believe. Oh. Okay, so search is finding an orthogonal pair in quadratic time. Search is okay, actually finding the solution. Verifying is just verifying the solution. Okay, you can do this in big of time. Okay, so specifically for which OV problem we have d equals big of log n or big of log n square less than n. So search is taking me the lower bound for search is n square, at least n square लगे जा रहा है. But verify का upper bound is log n, like it, you don't need, you can't do worse than n, so there's still already an exponential gap between these. Okay, this is similar to p versus np. P set of problems that can be solved in polynomial time, np are set of problems that can be verified, verify solutions in polynomial time. Okay, then there must be assuming p is not equal to np, there must be problems in np that are not p. There must be a problem we can verify solutions in polytime, but we cannot find solutions in polynomial time. Okay, so there must be problems that we can verify solutions in polynomial time, but cannot find solutions in polynomial time. Okay. Correction between P, NP, and OV. Sure, cool. Problem A is NP hard if every problem B that belongs to NP can be reduced to A in polytime. Okay. Every problem B in NP. Okay. Is all going to solve. Okay. Problem is if A is NP hard, then and assume we can solve A in polytime, then every B can be solved in polytime. Okay. Okay, I see. Okay, a problem is NP hard if every problem B in NP can be reduced to A in polytime. Okay. A problem is NP hard and A belongs to P, then NP equals NP. If P not equal to P and A is NP hard and A does not belong to P. Okay, whatever. I don't get this honestly. I need to think a bit more on this. There's the Cook-Levin theorem on 3-sat. K-sat is NP hard for K. There's some clause and shit. Can we use sat to prove a conditional lower bound? Okay, you know what? I'll just pause this here. I'll just do like, okay. 333. Finished PDF 19. First few pages that are relevant till exam 3. Cool. This is done, honestly. I am thinking if I can spend my time in reductions, like some ideas on the reductions, maybe review some assignment questions and how some reductions were done, what directions the reductions had happened in. I know the gradient is very lenient. Maybe I'll go and pee real quick. That could be fun, I guess. Yeah, I'll be back. I'll just pee real quick. This is nice and warm, honestly. Why? Why do that to me always? Okay, cool. So I think I'm gonna wrap up in 20 minutes. Okie dokie. And then in 20 minutes I'll wrap up. I will do like an hour of gym, maybe not an hour, maybe like 10 minutes of gym, and then I'll see where to go next. Cool. So Not algorithm design. Not this. Not this. Okay, actually, I just want to see one of the previous exams with solutions. Maybe does it have the solution? No. Okay, I think this is the one, right? Okay, so this is like one of the previous exams. I'm just checking in. So max, we know max function is the Lipschitz because it's just okay. Max is the Lipschitz because we just know that the first derivative uh, does not exist honestly, but it's still upper bounded by some constant L. Whatever. L Lipschitz and L smooth. This is pretty good, I guess. Fine grained complexity. Okay, so look at this. Like assuming OV, that means OV is going to. We are trying to solve OV conjecture using triangle detection, for example. And here we are claiming that we create a graph, and there's like an n squared loop. The moment you have an n squared loop, this entire thing becomes invalidated because you're saying that, hey, you know what, this is an n squared loop. Why are you doing this? You don't need to, and that's when you throw things out of the window. Okay. This is exam one, I guess. Does this have problem solutions or something? No, right? Okay, anyways, we'll just go through this maybe. So we get it. Like the okay, let's understand the inputs. So OV conjecture is has inputs as vectors, set of vectors inputs, and yes or no is going to be the output. Here we have vectors as an input, which is good. Triangle detection, according to our cheat sheet, triangle detection. Uh, what are the inputs to triangle detection? Triangle detection should get like a matrix as an input, right? N by n matrix as an input, and then uh, the output should be again like an n by n matrix, right? So we first have to construct an n by n matrix, which is sure you could just do this, I guess. Triangle detection is a graph thing. Triangle detection is a graph thing. You're getting a graph or an adjacency matrix as an input. Cool. Uh, and now what you're doing is create an edge between left vertex j and j center vertex. Create an edge between ith center right vertex and jth center vertex. Okay, you're creating a tripartite graph. What is this tripartite graph thing, right? We had seen a trick where when you're going from a matrix to graph, like triangle detection needs triangle. You know triangle detection needs a graph and uh, graph as an input, and we have matrix as maybe or vectors as an input. So you construct a tripartite graph for triangle detection. Triangle detection का input के लिए उसको चाहिए graph as an input. Okay, tripartite graph for more explicitly. So this is construction of the tripartite graph. It's very straightforward. You can just reuse this every time. So you try to construct a tripartite graph over here, um, and the output of your triangle detection is going to be like you can technically get some true or false, but this does not do OV conjecture because the reduction is also in the wrong direction. But let's see. Not orthogonal, so sure. It does not find vectors that are orthogonal, sure. Assuming threesome, so threesome को सॉल्व करने के लिए हम नॉन नेगेटिव इंटीजर्स वाला थ्रीसम यूज़ करने वाले हैं, ठीक है. So input is 3 vectors, and inside this we want to give again another augmented 3 vectors. This is fine, and we are just saying that okay, this reduction is wrong because a minus x plus b minus x is a plus b minus 2x or c minus x. So there's this factor of minus x that we are not able to account for. So that's wrong. Cool. We'll screw the gradient descent once. Simplex algorithm will also ignore this one for now. Cool. Yeah, find gradient complexity, right? Okay, let's read the question first. in threesome problem you are given these three in of size n, it is conjectured, show that, ओके अज्यूमिंग समथिंग, सो अज्यूमिंग थ्रीसम, ठीक है, अज्यूमिंग थ्रीसम, तो तुम्हारा आउटर शेल हो गया थ्रीसम, तुम्हारा इनपुट तुमको आ रहा है ए बी और सी, ठीक है. Okay, show that the problem is no easier if you only have set S equals Z as an input. So inside you are using a single set. So you are going from three sets to one set. So your transformation has to be like you're gonna get A, B's and C's as three sets as an input. You have to construct a single set S and pass it forward. So you are doing max of this, and the reduction is this, return single set threesome. Cool. सो अज्यूमिंग होता है वो हमेशा आउटर रहता है, उसको रिड्यूस करना है किसी और चीज़ में, ठीक है. कॉम्प्लेक्सिटी एनालिसिस तो हम स्ट्रेट फॉरवर्ड कर दिए हो. तो ये ट्राइपर्टाइट ग्राफ वाली चीज़ें हो गई, ठीक है. नो, दिस इज़ नॉट ट्राइपर्टाइट ग्राफ, दिस इज जस्ट थ्रीसम. सो थ्रीसम का अपोजिट डायरेक्शन में भी हो सकता है कि तुम्हारे पास एक ही सेट है, तीन में बनाना है, तो तीन में बनाना है, मतलब इफ़ यू आर गोइंग फ्रॉम सिंगल सेट टू थ्रीसम, सो यू कैन बी लाइक ओके, A is S, B is S, C is minus S, and that could be a reduction maybe. करेक्टनेस में तुमने थोड़ा ऐसा चीज़ें बता दी है कि ऐसे ऐसे करूँगी मैं, ऐसे ऐसे करूँगी मैं. ये ट्राइपोटाइड ग्राफ वाले पंगे बहुत ईजी है कि तुमको किधर भी ओवी तो बहुत सिंपल है, राइट. ओवी का सिंपल सीन ऐसा है कि देखो दोस्तों, my jange hurts. My jangs hurts. It's hurted so bad, bro. Yeah, my body is like low-key breaking down little by little. So it's not that, there is no wrong, nothing of that sort happening. I'm gonna be fine. I'm gonna be completely okay. Life is gonna be good. There is nothing to be afraid of. You just gotta keep focusing on your coding. Examination. Okay, so what I am doing is sure my friend, sure. Okay, cool. So this is fine, I guess. This fine grained complexity I'm trying to figure out, this is fine. The reductions are okay, I can figure out reductions easily. Okay, I'm good at reductions. Not really. Let me see other tricks that I had thought of. OV reductions, okay. If two vectors u dash v dash, you can do one to many. Okay, so if you have one, okay, so two vectors, if you have u dash or v dash, so you just add 0, 1. Okay. Yeah, I'm just gonna go to the assignment questions also for this, because assignments, I know they had like some really good problem statements, I guess. Regular expressions, I know. APSP min plus products के लिए क्या था, you had min plus and APSP is what? You have graph input. जब तुम्हारे पास ग्राफ है और min plus ग्राफ से ग्राफ को जाना है, APSP राइट, ग्राफ है, ग्राफ से मैट्रिक्स को जाना है, एडजेसेंसी मैट्रिक्स बना दो ना इसमें तुम, करेक्ट है ना. Okay, so algorithm for computing, there is a TN. Okay, if there's an algorithm for computing APSP on n node graphs in Tn time, then there is a ओके. सो इसमें क्या बोल रहे देखते हैं एक बार, इसका भी एक फ्रेजिंग अलग सा है थोड़ा, राइट. इफ देर इज एन एल्गोरिथम फॉर कंप्यूटिंग APSP ऑन n node graphs in time Tn, then there is a big of Tn time algorithm for, so I'm guessing this is APSP to min plus, right? Let's see. APSP ग्राफ है, ग्राफ से मैट्रिक्स जाने के लिए तुम बना रहे हो एडजेसेंसी मैट्रिक्स, और रिवर्स दिशा के लिए तुम बना रहे हो, राइट? इसका सोल्यूशन भी है ना, 7 का सोल्यूशन देखते हैं, चलो। प्रॉब्लम सेट 7 का सोल्यूशन मैं दिखाऊंगा अगर, राइट? गिवन मैट्रिसेस ए बी, ओके ओके ओके, होल्ड ऑन। सो तुम बोल रहे हो मुझे, ओके सॉरी, तुम मुझे बता रहे हो यहाँ पे, यार रुको यार तुम, राइट? I'm just gonna open this in the new tab maybe, we'll see। तुम मुझे बता रहे हो इफ़ देयर इज़ एन एल्गोरिथम फॉर कंप्यूटिंग APSP ऑन n नोड ग्राफ्स इन Tn टाइम, अगर Tn टाइम दिया है, Tn टाइम में तुम कर सकते हो, तो APSP है वो तुमको मालूम है कितना, ओके? अगर इफ समथिंग कैन बी डन इन Tn टाइम, देन दैट्स B, दैट इज यू हैव टू रिड्यूस min plus 2 APSP, ऐसा है क्या? लेट मी सी द सोल्यूशन भाई। ओके, सो यू आर सेइंग दैट min प्लस को तुम ट्रांसफॉर्म कर रहे हो, ओके ओके ओके, दिस इज अनदर इंटरेस्टिंग फ्रेजिंग, दैट अगर तुमको मिला, किसी ने किधर बोल दिया कि Tn टाइम एल्गोरिथम है तुम्हारे पास, ओके? इसमें भी ऐसा है क्या? लेट्स सी, से QR कोड प्रॉब्लम डिटेक्शन इज इन Tn टाइम, सो ओके, सो अगर Tn है तुम्हारे पास, तुमको अगर कोई बोल रहा है कि some problem can be solved in some Tn, then that problem is B and A has to be reduced to B, right? So अगर मैं इसमें ये पैटर्न में देखूँ यहाँ पे, तो मुझे दिख रहा है कि मुझे दिख रहा है कि APSP is Tn, so I have to reduce min plus to APSP, which is min plus will get me matrices and APSP operates on graphs, right? So I have to go from matrix to graph, तो ट्राइपर्टाइट ग्राफ, ठीक है? मैट्रिक्स टू ग्राफ जाते हैं हमेशा हम ट्राइपर्टाइट ग्राफ बनाते हैं, और ट्राइपर्टाइट ग्राफ टू मैट्रिक्स जो उल्टा है, ग्राफ टू मैट्रिक्स होगा, इसमें एडजेसेंसी लिस्ट बनाएंगे, करेक्ट? ओके ठीक है, लेट्स सी द अदर वन। ओके, रिपीटेड स्क्वेयरिंग, एडजेसेंसी लिस्ट का स्क्वेयरिंग करेंगे, ठीक है? तो ये समझ चुका हूँ। Tn जहाँ पे आता है वो B हो जाता है, ठीक है? वो सिंपल है, वो एक बात हम पक्की समझ चुके, तो लिख देते हैं यहाँ पे, ठीक है? assuming for example, let's just take phrasing, अच्छे से थोड़ा दिखता है, थोड़ा है ना, this assuming some conjecture B equals B के लिए जो भाषा यूज़ करी थी हमने वो थी B के लिए जो भाषा यूज़ करी थी वो क्या है? कंप्यूटिंग algo in Tn टाइम, और टिपिकली हम क्या करते हैं, A input transform give to B reduce get b out and transform a out. Okay, trick to identify the direction of reduction. Okay, so ग्राफ से तुमको मैट्रिक्स को जाना है तो एडजेसेंसी लिस्ट बना दो और स्क्वायर्स कर दो या फिर रिपीटेड स्क्वायरिंग कर दो। अगर एडजेसेंसी लिस्ट से मैट्रिक्स की तरफ जाना है, सॉरी मैट्रिक्स से ग्राफ की तरफ जाना है तो ट्राइपार्टाइट ग्राफ बना डालो सीधा सीधा। क्यूआर कोड डिटेक्शन में भी कैसा देखते हैं आप है, क्यूआर कोड डिटेक्शन में हम सेइंग कि क्यूआर कोड डिटेक्शन इज इन टी एन टाइम, सो दिस मीन्स टी एन इज क्यूआर कोड डिटेक्शन इज बी and we are saying that triangle detection has to be done in something. Okay, so QR code detection is it's like a matrix input. My matrix input लगेगा उसको और मेरा जो ट्रायंगल डिटेक्शन है उसमें ग्राफ इनपुट आएगा, राइट। सो ग्राफ टू मैट्रिक्स जाना है मुझे, करेक्ट। ग्राफ टू मैट्रिक्स होता है हमारा एडजेसेंसी लिस्ट का स्क्वेयरिंग और फिर एडजेसेंसी लिस्ट को ट्रांसफॉर्म करते, करेक्ट। लेट्स सी, सो रिडक्शन एम बी द एडजेसेंसी मैट्रिक्स, कूल। एडजेसेंसी मैट्रिक्स को ग्राफ में बना रहे हैं हम, ठीक है। इनपुट क्या है हमारा, श्योर किस कलर की चड्डी पहने हो, सॉरी माय बैड ब्रो, आई शुड बी जोकिंग अबाउट दीस थिंग्स। डॉग, ओके, होल्ड ऑन dog, hold on Jimmy, hey hold on bro, Habibi George Bush mata ibu, hold on। सो क्यूआर कोड डिटेक्शन में क्या बोल रहा है कि गिवन ग्राफ जी, बहन का लंड भाई, हाँ ठीक है। ट्रायंगल डिटेक्शन, सो ग्राफ टू मैट्रिक्स जा रहे हैं हम, राइट। ग्राफ टू मैट्रिक्स हमेशा एडजेसेंसी लिस्ट के साथ मस्ती करके होता है, राइट। एडजेसेंसी मैट्रिक्स बना दो जो कि मैंने बोला था, तो उसने एडजेसेंसी मैट्रिक्स लिया, डायगोनल एलिमेंट को एम बना दिया, क्यूआर कोड इन एम लगा दिया, इफ एग्जिस्ट ट्रू, ठीक है, करेक्ट है, ओके कूल फाइन। और explain why under the Boolean matrix multiplication conjecture no algorithm for QR code detection can have big O of under the Boolean matrix multiplication conjecture, assuming और under basically कुछ नहीं, ये तो सिंपल सा आर्ग्यूमेंट है। तुम बोल रहे हो कि तुम्हारा BMM जो है, assuming we have some subquadratic time algo for QR code detection, then we can solve triangle detection problem also। अगर क्यूआर कोड हो पाता तो बूलियन मैट्रिक्स मल्टीप्लिकेशन इज ट्रायंगल डिटेक्शन, सब अज्यूमिंग ऐसा बोल रहे हैं हम, ठीक है। और नो एल्गोरिथम, ओके, सो बाय थ्योरम फ्रॉम क्लास रिड्यूसिंग BMM टू ट्रायंगल डिटेक्शन, दिस मीन्स BMM इन बिग O of 3, ओके। ओके, ओके, सो वी आर सेइंग दैट, देखो मेरा जो वी नो दैट जो ट्रायंगल डिटेक्शन है वो खुद ही लेगा, वो सब क्वाड्रेटिक टाइम तो नहीं ले सकता है बिल्कुल भी, रिड्यूसिंग BMM टू ट्रायंगल डिटेक्शन। दिस मीन्स वी सॉल्व BMM इन, okay, assume we have some subquadratic, stop bro, stop, okay, assume we have some subquadratic time algorithm for QR code problem for some constant epsilon greater than 0, then okay, अगर okay, we are assuming the contradiction कि अगर मेरे पास सब क्वाड्रेटिक सब क्यूबिक, सॉरी, सब क्यूबिक टाइम एल्गोरिदम होता टू सॉल्व माय क्यूआर कोड डिटेक्शन, तो मैं मेरा ट्रायंगल डिटेक्शन भी कर पाता सब क्यूबिक में। बट बिकॉज कंजेक्चर बोल रहा है कि देख बीएमएम ही खुद रिड्यूस किया ट्रायंगल डिटेक्शन को, तो सब क्यूबिक नहीं हो पाता, तो मेरा कॉन्ट्राडिक्ट हो जाएगा। And then you're saying that I'm lying then. Okay, cool, got it. Let's see, so I'll just make a note here. 3:58 a.m. finished going through reduction examples and tricks, techniques, etc. Cool. So ये तो कर दिया हूँ मैं, अभी मैं क्या करता हूँ? Cool, I think I'm done with this. I'm just gonna stop streaming now. This was It was good talking to you all. Actually, you know what, 2 minute है मेरे पास, तो might as well just थोड़ा exactly 4 बजे कर दूंगा। बैंड का लंड भाई। Analytics, let's see, do I have any new... How are there already 3 reads, bro? Who is reading my blog so enthusiastically, right? Anyways, dog, चल ठीक है, I'll check if I have any notifications on LinkedIn maybe. Okay, this is so boring, bro. Why is this dude shit posting? Yeah, dude, people are gonna ask you like, why have you put on a picture which is like lopsided? It just hurts to see, bro. Honestly, dog. Come on, HEIC, you can't. You're not letting me use an HEIC. Come on, bro, that's crazy. Okay, I guess 401 is fine. Cool, folks, I'm gonna stop streaming. Bye. What a stream.